I'm Francesco Boy, and this is Just for Fun. Hi, and welcome to episode number 22 of Just for Fun. Today we're going to be learning how to do performance analysis of a program. And now when I say performance analysis, I'm sure that most of you are already thinking about pprof. And you're not wrong, we will see pprof a tiny little bit, but we will mostly be using a different tool that you might have not heard about, which is the tracer, the Go tracer. The whole idea being that pprof allows you to see what the program is doing when it's running on the CPU, but the tracer allows you to see what the program is doing when it's not running on the CPU, which is also really interesting. It allows you to understand problems or to identify problems that otherwise will be really hard to identify with pprof. Does that sound fun? Let's get started. Okay, so today, instead of writing all of the code from scratch, I actually have a piece of code that is already written. It's pretty simple. It's only 70 lines of code. What it does is, let's make it a little bit bigger so you can really read correctly. So there's the main function, creates a file, creates an image, and then encodes that image as a PNG to the output. It encodes it to the output, which is out.png. Create image, what it does, it creates a new image, a new gray image, and it simply goes pixel by pixel calling set on that pixel. And the interesting function is that pixel function that returns that color. And this color is basically something that I copy pasted more or less from the Wikipedia page for the Mandelbrot set. And if you've never seen a Mandelbrot set, you're up to something really cool because it's really fun. And basically what I do is a bunch of computations to decide what color they should be. This is pretty heavy computing wise, which is the whole point, right? Like we're gonna try to see, can we make this faster? Can we make this whole program faster? So pretty simple program. Let's run it. So go run main.go. We will see that it's going to generate a pretty big image. Let's see once it's done. So the image, it has 2048 of an 8-bit grayscale. So the size of the image is, I always forget how this works. Lowercase h. Lowercase LH. There you go. 282K, which is pretty big. And we can show it with image cat. There you go. Or we can also open it so we can zoom in, because I'd say it's worth zooming in. And look at this beauty, so cool. So the whole idea is that you have this fractal, right? Like if you zoom in, this shape here is similar to this shape here, which is similar to this shape here, and so on. So it's really cool. If you had never seen a Mandelbrot fractal, I recommend going to YouTube right now. Well, you're on YouTube. Going to another video on YouTube and just look for something like infinite zooming in into Mandelbrot set, because it's amazing. Anyway, the whole idea today is not to make cool fractals, is to make fast programs. So let's see, how fast is this? Well, one way of telling how fast it is to simply do, okay, let's run this. Time go run main.go, and we are actually counting how long it takes to compile the program too here. So let's do, I'm gonna call it Mandelbrot because that way it's clear that what we're doing. So if I do time Mandelbrot, we will see that this takes still around 5 seconds. I'd say a little bit more, a little bit less than 5 seconds. So 4.62 seconds. Cool. So how can we make this faster? Well, to understand that, first thing we need to do is to understand why is this slow. So we need to do some performance profiling. The easiest way to do it in this program is to simply add pprof trace. And how do you do that? Well, it's as simple as doing, let me import runtime pprof. And once you've imported this, you can do pprof.start CPU profile. And normally you should create a new file, but since we're not printing anything to standard output, I'm just going to send all of that to standard output directly. Not necessarily a good idea. Be careful with these kind of things. But for this example, it's the simplest thing. And then I need to remember to stop it. Stop CPU prefile. Cool. Okay, so now that we have this, if we compile it again, and then we run it again, and we send the output to cpu.pprof, it should take around the same time, should take around 4.7. So oh, it actually took a little bit longer. Look at that. Why? Well, because we're actually writing way more things. We actually create the trace itself, right? So it makes sense that it takes a little bit longer, but it's not crazy. But so what do we do now with that pprof? Well, we can do go to pprof, cpu.pprof. Now, this will work only if you're Go 1.9. If you're before Go 1.9, you will need to do go to pprof, Mandelbrot, cpu.pprof. You need to pass the binary too. In Go 1.9, you don't need to do that anymore, which is pretty cool. Okay, so now we loaded that and we can simply do something like top. And we can see that we spend most of the time in main.go, but actually the interesting thing would be to simply do top cum for cumulative. And we can see that cumulatively we spend most of the time in main.go, main.go, main.go. Okay, this is, oh, sorry. main.go was a file. So in main.main, runtime domain, main create, main.pixel. So main.pixel we spend a lot of time, which kind of makes sense. But this is always kind of confusing for me to understand. So rather than using top, one of my things that I like is to do list. So you can do list main.main. And see that we spend most of the time here on creating the image. So we do list.main.create. You can see we spend most of the time executing this end.set. So we spend 10 milliseconds in this line itself, but 4.58 in the functions that we call from this line. And if we do list main.pixel, we'll see that we spend most of the time doing this thing. Also, a decent amount of time allocating colors. Probably there's a better way to do that, but I do not care really. We spend most of the time in this, so let's try to optimize that, right? Now, how do you optimize that? Well, I don't know. This is the fractal algorithm, right? Like I cannot really change it. Otherwise, I will not be computing an algorithm. So does that mean that I cannot make this program faster? Well, you could try to optimize the multiplications here and maybe try to even recompile this and to write this in assembly and go for like crazy optimizations. And maybe you will make it faster. But I think that the biggest problem here is a different one. Can you even imagine what problem this could be? Pause the video and think about it for a little bit. Like, why could this program here be so slow? Well, actually, the biggest problem is that we don't know. And how can we tell? Well, instead of using the pprof profiler, let's try to use something a little bit different. Pprof, what it does is it asks regularly the program, what are you doing? What are you doing? And every single time it gets an answer, it adds it to its statistics. And at the end, we basically get everything together and we figure out, okay, so you spend most of the time, like 3 times out of 5 that I ask you, you were running main.pixel. So main.pixel spends a lot of time executing. Now, the problem is what happens when your program is simply not executing anything? Well, then you cannot see it. That's a problem. So what else could we do? Well, the tracer, what it does is rather than asking, hey, what are you doing? What are you doing? It does the opposite. Just say, hey, every single time you do something, let me know. Now that is very different, right? Because instead of generating a given amount of data, like saying, I'm not sure how often it does it, but I'd say it's probably like around 30 or 50, maybe 100 or 300. Actually, I have no idea. Times per second. What you're going to do is however often an event happens, it's going to be logged. And then you're going to visualize that. Cool. So that's the theory. But how do you use it? Well, it's actually really simple. So instead of runtime pprof, you're going to do runtime trace. So you're gonna do trace.start into the output and defer trace.stop std out. Okay, that's it. Now instead of generating a pprof profile, we will be generating a trace. So let's do that. Let's exit pprof, compile again, and then we're going to run the thing into a trace. M.trace, M for Mandelbrot. Okay, and before it took 5 seconds, something like that. Oh, this is actually really fast. That's even surprisingly fast. Okay, but it's around the same time as it was taking before. Cool. So now we have a file, which is our m.trace. And if we see all of these files, you will see that the trace itself is already 21Ks. So it's 7 times bigger than the profiler, which, you know, that's something we take into account in this case, is the tracer creates more data. But in this case, it's not that bad, really. Okay, so how do we open that? We're gonna do go tool trace of m.trace. And this will open a browser. This browser allows you to have a bunch of things. Some of them come from pprof, but the most important one is the trace. So when we click the trace, all of a sudden now we're gonna see all of the things our program did during the whole life of the program in this case. We can see how many goroutines we had. Let me zoom out a little bit so you can actually see things. Okay, so you can see how many goroutines you had. So you had 1 goroutine running. You can see the heap going up. And at this point right here, let's zoom in right there. You can see how there's a garbage collection. You can see it's a garbage collection because the heap goes down. Also because you have the garbage collection running. And you can see the garbage collectors will run in between processor 0, 2, and a little bit of 1. I think, looks like it. We can zoom in even more. Yeah, mark termination, processor 1 did a little bit. Now, look at the top here. This is microseconds. So we have an amazing detail here. pprof will never be able to show you that. Okay, but this is really cool. But what do we do now? Like, what do we do with this information? Well, if we zoom out, maybe not that much, you will see that if we, given all of the processors that we have, 0, 1, 2, 3, 4, 5, 6, 7, my Mac has 8 cores. Most of the time, only 1 is doing anything, which is a problem, right? Like, this is indeed a problem. The problem is that we don't have enough concurrency, and we should add more goroutines. So how do we add more goroutines? Well, it's simple. We just add go. But where? Well, let me create a new function. I'm gonna call it, let's call it create pixel. Okay, let's call this create sequential. So this one is doing 1 pixel at a time. This one is gonna be called create pixel. So create pixel, what it's going to do is it's going to run all of these in concurrency. Now this code is wrong because we're not even waiting for it to finish. So we need to also wait for all of these things to finish. We can do something like we're gonna create a wait group, sync.wait group. We're going to add all of the pixels, so width times height, and at the end we're going to do wait.done and wait. So okay, so now what's gonna happen is that we're going to create 2048 times 2048, which is something like 4 million goroutines, which is crazy. And we're going to then wait for all of them to be done and return the image. Let me do this create pixel. Okay, this looks like this might compile. So that is the code. Let's close that for now. Come back here. Build and run it. We're gonna call it px.trace because now we're doing pixels. Okay, how fast this should be, right? Well, it's around as fast as before. It was 4.6 before, and now it's 4.49. What about the data we ended up having? Well, we went from 21K to 87 megs, which is a lot. All of a sudden we have 87 megs, and that's actually even a problem because I'm not sure if GoToTrace will work very well with such a big trace. But let's see. At worst, I will edit this out so it will look like it's only 5 seconds, but this is probably gonna be more than a minute. I just noticed that this is using the log package, so you will see the actual timestamps there. So you will see how long I've been waiting for this to happen. By the way, thanks to 99 Designs in Melbourne for such a cool t-shirt. I went to visit them. They're using Go. Woo! It finished. Yay! Okay, so you will see that now view trace appears a bunch of times, and this is because there's a trace for the slice of data that basically Chrome will be able to handle. So let's get one somewhere in the middle. Let's get this one here. And now this might take, again, a pretty long time because Chrome needs to load a lot of information. And now you don't have a timestamp, so I will just wait for you. I'll let you know how long it takes. Okay, so it loaded, which is good. You can see a bunch of things going on in here. Interesting things that are going on is the CPUs are really full, which is good. So you can dig in and see that actually they're not that full, which is interesting. Also, we can see that there's between 1 and 9, so there's 9 Go routines that are runnable there, but only one running. Looks like most of the time there's actually only one Go routine running, which is surprising, right? Because we created all of them. Like, we have enough to be running, right? Also, we have some weird peak. Let me see. I saw there was a peak right there. Zooming into that peak. So there we got 7 running and 42 ready to run. And that looks like pretty good. Like the server is, like the CPUs are pretty busy at that point. But I'm not very convinced this is really good. And why this could be? Well, one of the reasons is the fact that you can see how many Go routines we created that are not ready to be, run, but we cannot run them yet. And there's 2 problems with this. One is we're allocating a lot of memory, and you can see it by simply going in 100 milliseconds, we went all of this way up, which means that we're gonna have garbage collection super often. So that will not be very good. But even worse, by creating so many Go routines, 4 million Go routines, I remind you, it's the fact that the program even finished is pretty amazing. By running 4 million Go routines, what you're doing at the end is forcing the scheduler to do a lot of work. And I think that is why you see so many gaps in here. That is actually contention of the scheduler trying to figure out of all of those 4 million Go routines, which one should be running. Is a lot of pressure. Also, even just creating those 4 million Go routines puts a lot of pressure on the runtime. So, okay, this is not a great solution, right? Woo, look at that. That is cool. 145 Go routines waiting to be run. So yeah, that is not amazing, right? Okay, so what can we do to make this better? Okay, so one solution is, let's say that instead of create pixel, I'm going to do basically the same thing, but with create row. And so instead of creating 100, instead of creating 4 million routines, I'm going to move this inside here. So now we're gonna create only 2048. So basically, when we're going to create 1 Go routine per row. Okay, so will this be very different? Well, let's see. create row. Okay, so go build dash o Mandelbrot, and let's call it row. What? That was incredibly fast. Whoa, really? Okay, it did not work. Okay, that makes more sense. Let's see the code. That was way too fast to be correct. Create row. Oh, I see. I think I see the problem. And actually, this might also be the same problem here. Yeah, this might be a data race actually. Because ing change, so ing should be here. As you can see, ing are actually referring to these two variables that keep on changing. So by the time the goroutine runs, might be completely different. So let's check that create pixel creates something that looks good. Okay, so let's make sure that our program with create pixel still works correctly. So let's run it again and cut the image. They should work. They should look like okay. And actually, let's time it too. I'm curious about how long it takes. So it's taking with create pixel 6.5 seconds. What about if we move it to create row? And let's make sure that we removed that data arrays we had. So we're going to pass int and I here and call create row. Cool. So let's do the same. Let's not keep the trace just yet. Just let's see how long it takes and go build. Otherwise we're trying the same. And I'm gonna run it and whoa. Okay, so we went from 6 seconds to 0.7972 seconds, which is amazing. We're still taking 4.68 seconds total time, but we're distributing it across all the CPUs really well, apparently. Let's create the trace. So let's create row.trace and see, that's amazing. So go tool trace, row.trace. Okay, so, and now we see it, and we'll see that, okay, there was one garbage collection in the whole thing, which is pretty cool. The CPUs work really well. You can see that there's basically no gaps. There's, how many goroutines we have? Let's see, we zoom down. There's 770 goroutines waiting to be executed, which is a lot, right? But it is not 4 millions. So the Go runtime is able to handle that with ease. Clearly, everything looks perfect. Let's see that garbage collection. Where was the garbage collection? Right there. That is the garbage collection. In the garbage collection, you can see exactly what happens and what threads are doing what, which is pretty cool. And see that it took 382 to 383, took basically like 1 millisecond, the whole thing, which is pretty impressive, to be honest. Okay, cool. So that is actually probably better than I expected. To finish, let's see if doing a different kind, which is rather than using per row, but creating just 8 goroutines will make it faster. So to do that, what we need to do is, I'm gonna call it create workers. And so let's actually copy this. And let's copy also, actually I'm gonna copy everything and then modify it from there. So we're gonna create the image. We're not going to use as wake group this time. We're gonna create instead a channel, and the channel will be a channel of pixels. Actually, a channel of pixels. Let's call it px, and the px is a struct that has x, y, int. So what we're gonna do is for every single pixel, we're gonna remove this, we're gonna remove this and this. We're just gonna keep that loop. We're going to send into the channel, we're going to send a pixel has ij. Okay, we're not waiting anymore. So that's going to do the thing, which is good. Now what we need to do also is we need to add someone to actually work, right? So we're gonna add 8 because that is how many CPUs I have on my computer. You could play with more or less, but that's the idea. We're going to create also a wake group, sync.wake group, and these goroutines, what they're going to do is they're going to iterate over the channel, and for every pixel, what they're going to do is call that thing. So they're just going to, we need to replace this by px.x, px.y, px.x, px.y. So, and then once we're done with all the channels, we do done. Then here we close the channel and then we wait. Did I call it? Yeah, okay. So the whole idea here is that we're gonna create 8 goroutines that are going to get pixels, as long as there are any pixels, and do the work. Once they're done, they all notify the wake group that they're actually done. On the other side, we're going to send all of the pixels to this channel, the channel up there. And once we're done, we're going to close it, which will cause the workers to finish, which will cause them to call done, which will cause them to finish this wait. All of this code will be on GitHub, so just go check it out. There's a link to the repo down here in the video description. Okay, so will this be faster? Also, will this work at all? So let's change it, create workers, and let's run it. So first let's compile, and now let's run it. So workers.trace. So it's slower than the one before. How slow? Really slow. Huh, surprising, right? Like this is incredibly slow. Negative wake group count. Okay, that is actually wrong. There's a bug. Let's see. Where's the bug? Oh, I did not do add. That's a problem. Add 8. Right? Yeah. Okay. So that's a problem indeed. Let's try again. Okay. Okay, so this way slower. This 12 seconds, which is weird because I expected this to be faster, right? Let's see what happened. Go to trace, workers.trace. And let's see how long this is going to take, because apparently we've done a lot of events that were logged and the trace is big. How big? Let's see. Workers are 96 megs. Whoa. Okay, so let's see what is going on here. As you can see, again, we have something really similar, right? Like we have that thing where it looks like it's really full, but then when you zoom in into it, you start realizing that there's not that much that is being done. Most of the time, we're not running anything. Interestingly enough, though, we only have 8 goroutines, so it's not the runtime having too many goroutines. But, you know, we talked about contention before, saying that the runtime was not able to deal with so many goroutines, creating some contention. And that is a problem again, actually. If we go back to here, we can see that we have synchronization blocking profile. And that is actually pprof. And pprof tells us that we spend 50 seconds. With that, we spend 50 seconds waiting for something. What were we waiting for? Well, we were waiting in create workers, and that is actually the channel we created. That channel is creating a huge contention. Why? Well, it kind of makes sense, right? We are sending things into the channel in a blocking way. Every single time we do this, we need to wait for someone to be on the other side to get it. And at the same time, every single time someone wants to get something, we need to be ready to send it. This creates a lot of contention. So maybe what I think is that we should try to simply add with times height here, right? Like now if we make the channel as big as the pixels we have, there's gonna be a pretty big allocation, but there's only one. And then there will be basically no contention. So let's try that. Let's see if it works very differently. So let's compile it again. And let's run it. Workers buffered. And let's see, before it was, whoa. Okay, so we went from 11 seconds to 1.2 seconds, which is way better. So we removed a lot of that contention. Let's open the trace, workers, buffer trace, and it works really fast. The synchronization broken profile went to 600 milliseconds from 50 seconds. that is amazing. We removed most of the contention, and the trace looks much better. There's the Goroutines, they're mostly running all the time, and all of these looks really homogeneous and full of things running. So that is really good. And heap wise, yeah, the heap is bigger because we created a big channel, but at the same time, we didn't even run the garbage collector once. So that's pretty cool. Could we do better than this? The problem that we have, the contention that we still have left, those is 100 milliseconds, then I feel like maybe we can shave them away, is the fact that we have too many tasks. Every single task is too small. So what if instead of sending this, we change, so the workers, what they're going to do, and I'm going to create this in a different function so that you can, I'll keep all of this in the code so you can read one at a time. What we're going to do is create big workers, I'm going to call them, create row workers. So rather than sending pixels, we're gonna send the row. So just an integer, so that's going to be sending just I. And so that's 2048 tasks, which is way less tasks than before. Now what we're going to be doing here is we're going to actually need to do that thing here. So that's going to be I. That's going to be J. And actually I can copy the thing from here. At what point did I delete this? So yeah, otherwise we're not doing anything, so that's why. Okay, so we create the channel, we create the workers work per row, and then we send the rows. That looks better. So let's do it again. Okay, so that is really good. So times, that is workers per row. Ooh, I'm buffered. Or buffered. No, I'm buffered. What if workers per row buffered? Row buffered. I feel like that's gonna be the fastest one. Let's see. I'm excited about this one now. So let's do width, which is whatever. We're doing square, so we don't really care about which one it is. Let's see, and woo! Okay, so that is, it's almost as fast as the other one. Let's see the times. No, oh, okay, I want to copy the whole thing. Okay, so the winner is per row, but actually makes sense because we're still doing it per row, but before we did not have any synchronization really. We just created 2048 Goroutines, and everything just works. This one is pretty close, so very cool. And in this one, we only create 8 Goroutines. So I'm gonna leave all of these there I will add it to the README in the repo. Go check that out if you want to. I think this is really cool, really exciting. So with this is the end of the episode. Thanks so much for watching. I hope you liked it. Let me know if you like these episodes where I'm showing more like tooling and stuff like that and performance concepts. Maybe it helps. Maybe you prefer just to see me writing more code and code reviews. I don't know. Let me know here on the comments, on Twitter, or at forum.justforfunc.com. So as always, thanks for watching and see you all in 2 weeks.